we will continue on the course on biostatistics and design of experiments. So as I mentioned in this course, I am going to talk about biostatistics, that is the part 1 of the whole thing, and then comes the design of experiments. In biostatistics we are going to look at a large number of distributions like a binomial distribution, Poisson distribution, Weibull distribution, T distribution, Z distribution, normal distribution and so on. Then we are going to look at something called confidence interval, test for normality, test of significance, different types of tests, T test, F test, ANOVA test, and under T test you have one sample T test, two sample T test, and then we are also going to look at chi-square test or chi-square distribution. Then we are going to look at non-parametric test, another type of tests that are possible in biostatistics which does not need to have a normal distribution. Then under design of experiments we are going to look at one factor at a time. How do I change one factor, like if I am changing temperature alone, then after I finish temperature optimization I go to pH alone. So that is called one factor at a time, and then go into a design, full factorial design, where I am changing many factors simultaneously. Then there is something called fractional factorial design, where you are doing a fraction of the full factorial design, that means you are cutting down on the experiments. Then we are going to talk about what is this confounding and alias, and how does confounding affect when you start doing the design of experiment. Then there is something called screening designs, and that is initially you start looking at a large number of parameters and carry out experiments, that is called screening designs. Then you come to second order designs, that means non-linear type of designs. Then once you collect the data from the design, you do a regression analysis, mathematical modeling, then finally you go into data reduction. That is the second part of the course. The first part is biostatistics, second part is design of experiments. Okay, let us get into and before that, these are some of the books which may be very useful for you. Biostatistics, an introductory text but by Goldstein. Then we have Barlow, a guide to the use of statistical methods. Then this Fisher and Yates, this is very good book which gives a lot of statistical tables, because as you go along you will come across a lot of tables, T tables, F tables, random numbers, odds ratios, confidence intervals, p values and so on. So no, for all these you need to have some tables, and this one gives you. Of course you can get the tables online also, but they are all based on this particular book called Fisher and Yates. They have developed statistical tables for biological, agricultural and medical research. Okay, let us look at data types. There are two types of data. One is called the attribute data, other one is called the variable continuous data. Attribute data could be like 0, 1, pass, fail, alive, dead, black, white. So it is like numerical numbers. Okay, it could be in counted, 10 defects in 10,000 samples, 10 failures in a class of 100 students. So you can count it, you can classify it. So it is based on numerical numbers. So it is a discrete. Whereas in variable data, continuous data, you can have continuously changing. For example, I can measure temperature of a fermenter continuously. I can call it 26.5 or 26.6, 26.7, 26.8, like that. I can measure the temperature very continuously. Similarly, I can measure the pH of the solution in a very continuous manner, 3.1, 3.2, 3.3 and so on. So that is called the continuous data. So we have the discrete data, we have the continuous data. So any data type can be divided into these two forms. Now under this discrete, we can classify it as defective or not. So especially if you take a factory where they manufacture a lot of products, for example they are manufacturing screws and they would like to have the screw of 10 mm diameter. So any screw that is not 10 mm, if it is 9 mm or if it is 11 mm, it is called a defect. So we can say out of 1 million screws that are manufactured in each week, there could be so many screws, 10 screws which are defective. That means they do not have 10 mm as the diameter could be different. Okay, so that is classifying. So you have something called the binomial distribution coming into picture. So there are 10 defective screws out of 1 million screws that are manufactured in this particular week. Then we also have something called Poisson distribution. This is again giving a count. Okay, there are 3 road accidents in the city of Chennai in a month's time. There are 4 people suffering from HIV in this particular village in South India. So, you are giving some numbers, and again data, the numbers are collected based on large number of samples. Okay. Again it is count, that is called Poisson distribution. Okay. So, we have the binomial distribution, out of 10,000 samples 10 are defective, or we have the Poisson distribution where I am saying there are 3 deaths per day in the city of Chennai. Then under the continuous data we have the normal distribution. You must have all heard of normal or the uniform distribution, which looks like a bell type of curve, and also we have the variable distribution, which discusses the life of a, say for example, a light bulb or a fan or a refrigerator. Okay. So, that is called the variable distribution. So, that is continuous data, we can measure the data continuously. Okay. That is called the variable distribution. So, we have 2 types of data, the discrete data and the continuous data. So, the discrete data is used for identifying how many defects are there in a sample, and how many accidents are happening in Chennai per month or per week, and so on. Okay, whereas continuous data, we are measuring the data in a very continuous manner. Okay, so in fact there are large number of distributions, much larger than what I talked about. So as you can see, don't get scared, we have normal distribution, we have uniform distribution, then we have T distribution, we are going to talk about this, we have F distribution, we are going to spend some time on this, then chi-square distribution, we are going to spend some time on this, variable distribution, okay, and so on. Actually, as you can see, these are all continuous distribution. We have fatigue life distribution, gamma distribution, double exponential, power normal, power logarithm, beta distribution, and so on. So a large number of distributions are there. They are used in different scenarios, different requirements, different problems, but I will be spending time on normal, I will be spending time on T distribution, I will be talking about the chi-square distribution, F distribution, variable distribution, but all these distributions are very useful actually. As you can see, and they have different shapes, and that means the probability of certain event happening will follow different type of relationship or mathematical formula. So these are all continuous distribution. In the discrete we have the binomial, and we have the another type of Poisson distribution. Okay. So these are continuous distribution. So I said we will spend time only on few of these, not all of them. Okay. Let us take binomial distribution. You must have all read in your school talking about probability, tossing a coin, tossing a dice, and so on actually. Okay. So binomial distribution is based on yes no or 0 1, success failure, pass fail, live dead, black white, or suppose I have a dice which has 6 faces, then I am throwing a dice, you may get a number 1 or 2 or 3 or 4 or 5 or 6 at equal probability. So all these are based on binomial distribution. Okay. So the sampling is carried out without replacement. Okay. That means you are not putting it back, so the draws are not independent. Okay. So binomial distribution is a good approximation here. So if I am tossing a coin, probability of a coin showing head could be half, probability of coin showing tail could be half. So if I throw it 10 times the same coin, if I want to know what is this probability, 4 of them out of this 10 is heads, I can use the binomial distribution. Okay. Or if I am going to say that the birth defect of children born in India is 10%, and I go to a village which has got 1000 children, what is the probability that 4 of these children will have that particular defect, birth defect? Then I can use a binomial distribution. So that way binomial distribution becomes very useful for us to do. So let us look at a simple problem, tossing of a coin. So I have a coin, as you know, I can get either heads or tails. Okay, heads or tails, that means equal probability, 50% probability for heads, 50% probability for tails. So I toss the coin 4 times. So I can get 0 head, that means all of them become tail. I can get 1 head, that means I can get 1 head and 3 tails. I can get 2, that means 2 heads and 2 tails. I can get 3 heads and 1 tail, or 4 heads and no tail. Okay. So all these are possible. and the likelihood of getting each one of them is given by this formula 1 by 16, 4 by 16, 6 by 16, 4 by 16, 1 by 16. How do we get this? In the next slide I will show you the formula. So this is how the distribution will look like. So I toss the coin 4 times, so obviously getting 2 heads 2 tails is most probable. How to get this number of 6 by 16 I will tell you in the next slide, and then getting 1 head and 3 tails or getting 3 heads and 1 tail are equally probable, which comes second, and then getting 0 heads or getting 4 heads again is less probable in this, but they are equal. So this is how the binomial distribution will look like. Now what is the formula for calculating this probability? Okay, let us show it in the next slide. This is how the probability equation looks like. The probability function fk is given by n factorial divided by k factorial multiplied by n minus k factorial p power k 1 minus p power n minus k. So n trials, k successes, p is the probability. So n times you are doing something and k is the successes you are talking about, p is the probability. So in the previous problem, like I am tossing the coin 4 times, okay, n will be equal to 4. If I want to know what is the probability for 0 heads, then k will become 0 and p is half because I can get either head or tail. So probability is p, which is half. Okay, so p is half, n will be 4, and if I want to get 0 heads, what is the probability I want to calculate? I will put k as 0. N factorial, you all know, must have studied, n factorial is nothing but n into n minus 1 into n minus 2 into n minus 3 and so on. Okay, so when I put k equal to 0, I substitute here, I will get 4 factorial, and the denominator I put 0 factorial, then I put 4 minus 0 factorial, half raised to the power 0, 1 minus half raised to the power 4 minus 0, that is what I have written here. Okay, 0 factorial is 1, 4 factorial is 4 into 3 into 2, okay, so that is 24, half raised to the power 0 is 1, 1 minus half is half, half raised to the power 4 is half of raised to the power 4. So this is 4 factorial at the denominator, so these two will cancel, these two will cancel, so we have half raised to the power 4, so that means 2 into 2 into 2 into 2 4 times, that is 1 by 16. So if you want to see 0 heads, when you toss a coin 4 times, the probability will be 1 by 16th. You see, that is what I had mentioned here, right, 1 by 16th. This is how you get the data. Now if you want to know what is the probability to get 2 heads when I toss the coin 4 times. So n equal to 4, k equal to 2, and again p will be half. Okay, so you put 4 factorial, 2 factorial, 4 minus 2 factorial, half raised to the power 2, 1 minus half raised to the power 4 minus 2. Okay, so you do all these calculations, you end up with 6 by 16. Okay, I mentioned here 6 by 16, that is the maximum. So when you toss the coin 4 times, what is the probability of getting 2 times head in that 4 is 6 by 16, that is the maximum. Okay, like that. So if I want to know with 4 times tossing, if k equal to 1, that means 1 head, what is the probability of getting 1 head when I toss the coin 4 times, I put n equal to 4, but I put k equal to 1, p will be half in all these cases. Okay, so 0 factorial you should remember is always 1. Okay, so it is simple to calculate. Okay, now you can do the same calculation using Excel as well. Excel has a function, okay, called binom distribution. This is the function, okay, binom distribution. There are 4 terms inside this, okay, 4 terms inside it. Number S is the number of trials, number of successes the trials is the total number, and probability S is the probability, and cumulative you can say true or false. If it is false, it will give you the, okay, it gives you the exact number, whereas if you put true, it gives you a cumulative number. Okay, so trials is n in the equation, number S is the success k, probability is your p, small p, and here we put true or false. If you put false, it gives you the exact answer. For example, in the previous problem where we looked at 4 times I toss the coin, I want to know 2 successes with heads. So what will I do? I will put 2 here, I will put 4 here, I will put half here, and I can put false here, and that will give you the binomial distribution answer. I should get 6 by 16 as my answer. Okay, let us look at it in the Excel as well. Okay, so this is the function I said, it is called binom distribution. Number s is the number of successes, so I will put 2 here, number of times I do, that is 4 here, probability is half, that means I put 0.5 here, and if I put false, it will give you the exact answer, whereas when I put true, it will give you summation of all the answer. Okay, so I will put false. So what did I get? I got 0.375. Now is it same as 6 by 16? See, so that is 0.375. So using Excel we can calculate the binomial distribution. As you can see, this is the equation. Okay, for example, so this is the number of successes, this is the number of trials, that is, this is n, this is k, this is the p, and here we put false to get the exact answer here. When you put true, it adds up, it is a cumulative answer. That means if I put true here, it tells you what is the cumulative probability for getting at least 2 heads out of 4 trials. That means it will look at 0, it will look at 1, then it will look at 2. So it will give you the summation of all these 3 things. So we can use Excel also to do the same calculation, or we can actually calculate it out also. Okay, so you understood. So you have a Excel function called binom distribution, and there are 4 terms here. The trials, this is equal to n, this is equal to k, this is equal to p, and here you put false to get the answer. Now there are many softwares which can do this job also. Some of them are commercial, there could be something free also in the net and so on. So I also looked at a software, okay, and there is this free online statistical calculator, and this is the link for that, you know, GraphPad. It's called GraphPad software. Okay, it can do a lot of nice calculations online. We put in some data and it can do some calculations. So I am going to use this, okay, and we are going to we can do some of the problems using this. Okay, so this online software, as you can see, can do a lot of calculations. It can look at binomial distribution, Poisson distribution, normal distribution. It can look at different types of statistical tests, t-test, f-test, and so on. Okay, so we are also going to use this. So this is the link to that, www.graphpad.com quick calcs. So let me show you that here. So when you do that, as you can see here, okay, this is the GraphPad quick calc. So we have the binomial distribution coming into picture. So we click on it and then we go continue. So when you continue, as you can see here, calculate different types of distribution. Let us go to binomial. We will talk about different distribution later. As I said, I am going to talk about binomial, I am going to talk about Poisson, t-distribution, normal, and so on. So here you have the binomial. So we say continue. Okay, so here you have the binomial distribution. How many trials? So we are doing 4 trials. 4 trials. What is the probability of success in each trial? 0.5. Calculate probabilities. So here you can see it gives you everything. So number of successes, 0 means it gives you 0.25, that is 0 heads out of 4 trials. The probability is 6.25, and then if you are talking about 1 success out of 1 head out of 4 trials, you get 25%, but here you gives you the cumulative. 6 plus 25 is giving 31. How do you, even in Excel, if you put true as the last term, you will get the cumulative, whereas if you put false, you will get the exact. So 2 trials, you get 37%, you can see, so 0.375. and the cumulative will be some 6 plus 25 plus 37 68%. So 3 successes out of 4 it gives you it is 25%, cumulative wise it is 93%. So all 4 heads out of 4 trials 100% it gives you. So we can use this particular online software also. There could be many online softwares, but I am looking at this particular online software because it looks good. There are many commercial softwares also, one can go about using them. So it depends upon whether you have the availability of these. There are softwares which may be even freely downloadable, but this is a simple online software where you give the data and it gives you the results. As you can see here in our problem, we are tossing the coin 4 times, and you can get heads or tails with the probability of half. Now out of this 4 times, 0 heads 6%, 6.25% probability. Out of 4 times 1 head 25% probability. Out of 4 times 2 heads 37.5% probability. Out of 4 heads 3 heads 25% probability. Out of 4 trials 4 heads 6.25. So I showed you 3 different ways by which we can calculate this, right. So one is using this equation, okay. So using this equation, so if the data is very small we can use this and do it. That means if the k, n and all is small we can, otherwise we can use the Excel function which is called binomial distribution, okay, where this is the number of successes, that is k, number of trials, that is n, and this is the probability, that is in this case half p, then here we give false. Or we can use this free online statistical calculator which I showed you. So we click here and then we give a number of trials as 4 and the probability is half. So it gives you the entire table. For 0 success out of 4 what is the probability, for 1 success out of 4 what is the probability, for 2 success out of 4 what is the probability, and for 3 success out of 4 what is the probability, and that is what it is giving you here, right. So as you can see, so it gives you in the entire table. So I showed you 3 different approaches by which we can do the binomial distribution calculation. Okay, let us go further. Let us look at a biological application, and 1% of the population is infected with HIV plus. I am just giving, so maybe in a country 1% of the population is infected. So there are no obvious symptoms, okay, that can be used to recognize the carrier. So we assume that if I look at somebody I cannot tell whether the person has HIV or not unless I do a detailed study, for example. So I need to select some people and do a detailed study. If the sample size is too small then I might not be able to find at all. Then if I take a very big sample then I need to do a lot of sample collection, sample analysis, so I need to spend a lot of money, that is also inefficient. So what do I do? Is it okay if I just take 20 people? Is this sample adequate? Will I be able to find at least 1% in that? Okay, so that is a problem. So how do I do using binomial distribution? I can use n equal to 20, I can say k equal to 0, that means I am in that 20 I am not finding anybody with that, and p is equal to 0.01 because I said 1% of the population. So p is equal to 0.01. So when I put it in binomial distribution, 20 factorial, okay, again this is 20 factorial because k equal to 0, k equal to 0, so these two will get cancelled out, p is equal to 0.1, k is equal to 0, this also will get cancelled out. So 1 minus p is 0.99 raised to the power 20, 0.99 raised to the power 20 gives me 0.82. So what does that mean? There is a 82% chance that if I take 20 people I will not even find one person with that disease. Did you notice that? It is very important finding. So there is a 1% population is infected with HIV, but if I take 20 people randomly there are 82% chance that I will not find anybody with that in that sample of 20. So I may say nobody is infected. So obviously what does it mean? My sample size is too small, okay. Or if I can say n equal to 20, k equal to 1, then I can do the same study and see what is the probability of finding at least one. So what it means is when I randomly select 20 people, I am not I will not be able to find even 1% with that particular disease. So, I may say that nobody is infected with this particular disease. Okay. Now, we can also check with the online software also, okay, using the same online software. Okay, for example, same thing for getting 0, it gives you 81% or 82%. So, if I want to find at least 1% with that, 98%, okay, will happen actually. Same thing we can do it using this. Okay. So, what we do, we will go to the graph pad and then I go back and I will put 20, then I will put 0.01, then calculate probability. So, as you can see here, there is, okay, 81% probability or 82% probability that not a single number of successes is 0, that means not a single person with that particular disease I will be able. So, obviously my data is too little, my sample size is too little, that I may miss out. Okay. So, you must be very careful when you select sample. A very small sample can make you conclude wrongly. Okay. So, that sample size is a very important parameter, and we are going to talk about that in other cases also as we go along. So, with the very small sample size, for example here 20 people with the 1% probability, I may say that 82% of the time there will not be even a single person infected with that disease in the sample of 20. So, you can see that we can show it using this equation, or we can go to that software GraphPad online and then get the same answer. Okay. Even with the Excel also we can do the same thing. So, we go to the Excel, okay. So, we go to Excel, so we type a binomial distribution, so fx, so we have binomial distribution, so we have number of successes, we are talking about 0, trials is 20, probability is 0.01, then we can say false or true, it does not matter, false, then okay. So, we get again you can see the answer is 82%. So, 82% of the time we will not be finding any infected person if I take a sample of only 20. Okay. So, you have to be very careful on that. Okay. 82% of the time we will miss out, we will come to a wrong conclusion. Okay. Let us look at another problem. A tranquilizing drug caused anemia in 2 of the first 10 patients who were tested. Okay. So, I took 10 patients and then I gave the drug. First 2 patients had some toxicity problem, but then a true toxicity of this kind is tolerable only if it does not affect more than 10% of the treated patient. So, but here the first 2 patients themselves had the problem. So, should the drug be withdrawn or tested further? Okay. So, only 10% of the patients can have this type of toxicity effects, but here with 10 patients 2 of them are having problem. So, should the drug be taken out? Okay. So, we are in a big problem. So, let us go for example the graph pad, then we will say 10 patient and then we want to say 0.1%, calculate probability. Okay. So, that is very high. Okay. So, we cannot conclude because it is showing almost very high probability, almost 34%, whereas we want to have less than we want to have 10% only. Okay. Whereas if I take a larger population, for example if I take n equal to 40, okay, if I take a larger population for testing and then I keep the same 10%, when I calculate the probability, okay, then as you can see here, so here if I go to 2% successes, okay, here it is still going to 14% probability, okay, the cumulative if you look at it is coming to again 22%, whereas if you want to have less than 5% as a possible number, then obviously if I go to say n equal to 100, okay, so if I go to n equal to 100, for example, suppose I take a sample of 100 patients and then do this study, okay, as you can see here, out of the 100 patient I can have up to 5 patients having toxicity, I will be within that 10% limit, but if I go beyond that I will have numbers going up, okay. So obviously what it means is the number of samples I have taken should be considerably large in order to prove that the toxicity is less than 10%, okay. So obviously in this particular case also you can see the sampling size has to be much larger. Okay, suppose let us look at another problem. 30% of the students wear glasses, okay, 30% of students wear glasses. So if I take a random sample of 10 students, find the probability the number of students wearing glasses is at most 4, okay, at most 4 means okay, so people different types, you can have people wearing glasses, you may get no one, we may get 1% wearing glasses, we may get 2% wearing glasses, we may get all the 4% wearing glasses, right. So we have 30% of students, so here p is equal to 0.3 and then you have n is equal to 10 and then you want to look at various conditions of 1% wearing, 2% wearing, 3% wearing, 4% wearing glasses, okay. So that will be the k values. So we can use this particular function, or we can even use the so I take 10 students, the probability is 0.3, so I calculate the probabilities, so as you can see here 0% wearing glasses, 1% wearing glasses, 2%, 3% and so on. So 0% wearing glasses will be 2.82%, but if you are talking about 1% wearing glasses, out of this 10 is 12%, 4% wearing glasses is 20%, okay. But if I add up all these, that means if I take 10 students out of this lot, students wearing 1 or 2 or 3 or 4% wearing glasses will be so many percent, 84%, okay, or 0 classes. So this is the cumulative and this is the exact probability here, okay. So you can use this quick calc of the graph pad to identify the probability distribution function for a binomial distribution, okay. So you can use this equation, or we can use the Excel function, or we can use the graph pad software also. So all these are possible to get. So as you can see here, this is the cumulative, this is the exact probability for 0% wearing glasses, 1% wearing glasses, 2%, 3%, 4%, like that, you know, it goes up to n of 10. Now let us look at another problem. Now there is a disease with known mortality 10%. What is the minimum number of patients required to demonstrate the efficacy of the completely curative drug? That means there is a disease of mortality of 10%, that means 0.1, okay. Survival if you take as pi 0.9, 1 minus 5 is death is 0.1, okay. I want to show completely curative, that means I do not want to see any disease, okay. So if I take n patients and survival probability for each of the patient is 0.9, so it will become 0.9 into 0.9 into 0.9 raised to the power n, Now this should be less than 0.05 because why? 0.05 is 5%, that means that gives you 95% confidence. Do you understand? So this mortality is 10%, that is 0.1. So survival is 0.9. If I call 5 survival as 0.9, 1 minus 5 death is equal to 0.1. Okay. Now if I take n patients, then survival for each one is 0.9. So 0.9 into 0.9 into 0.9, I do it in n times, that is why I have 0.9 raised to the power n. Now this should be less than, to get a confidence of 95%, this should be less than 0.05. Okay. So if I calculate this from this n, I get n should be greater than 29. That means I should have at least 29 patients and show on all of them none of them die. If I do that, then I have a 95% confidence that the drug has a completely curative effect. Okay. So this approach tells you how to select the number of subjects or number of samples in our problem. Okay. Okay, so we looked at many different cases where we use binomial distribution, and binomial distribution is based on successes when you take a sample of n. So k successes in a sample of n, and the probability of each one happening p. It tells you what is the probability of k successes in a sample of n if the probability for each event is p, and that is what is binomial distribution is all about. So we can use it like if there are 30% of the students wear glasses in a class, if I take 10 students, what is the probability that 4 of them will be having glasses. If I have a disease which happens 2% in India, if I take a family of 20 people in a house, how many of them will have this particular disease. So for all these we use this binomial distribution very effectively, and it is very useful. I also taught you how to use the binomial distribution using the formula n factorial divided by k factorial n minus k factorial, and then numerator p raised to the power k, then 1 minus p raised to the power n minus k. So we can do it numerically, or we can use the Excel. All of us have Excel. There is a function called binom distribution in the Excel where you can substitute and calculate, or you can use an online software called GraphPad. I showed you the link to the software. You can substitute the data and get the values. So all these approaches are possible, and you can see binomial distribution is very useful in clinical trials and large data analysis. Okay. The next class we will look at something called the Poisson distribution. Again, this is a discrete distribution which talks about events. Again, Poisson is an extension of binomial distribution. Okay. Thank you very much.